So this week is English. Screen share switched on. Desktop start screen share. That's happy. I'm not even going to try to switch on the Q&A. This is beautiful stuff, but let's close all of it. Okay. So let's just minimize that. And let's just go to the project page. Let's see, okay. And the project is, the description is still not complete. So really what is missing is the very last step. It's called step 6. And I must tell you what you need to do for extra credit and how it's going to be evaluated. And I'll do that shortly. But for Wednesday, I asked you to read the spec as it is, parts of it at least, the details, and that's still the same, basically. And for Friday, I didn't ask you to do this, but I suggested you do step 1, which is just to add the game over. And I showed you how that would look. And there's a special, I'm doing this as you are doing this, and there are a few special tricks you have to pick up sometimes. So there's a little special trick that you have to do. Otherwise, you get an exception, as Josh had an exception. And if you do it the wrong way, I checked, I also get an exception. But this step 1 explains how to do the game over so you don't get an exception. And so for today, I'm going to show you what happens after step 2. So the idea of step 2 is to add a super cat and a normal cat, as it turns out. So instead of just having one cat move across the board, you say, I'm going to use that one cat class that was part of the framework as a base class. I'm going to extend it to a normal cat into a super cat. One just moves faster than the other, nothing else. And so all the instructions are in there, and then you have this scenario where you have in this case, a super cat that moves faster. That's what the picture is supposed to show. And I can show you what it looks like when I execute it. This will be framework 2. Execute. So I'm trying to do this exactly as you would do it, and I'm trying to describe the problems that you would run into if you do this. And now there'll be slight issues with the board size again, but you should be able to see that there's a super cat that comes along, and it goes quite fast. I mean, the whole point of this was to just make a super cat. Okay. There's one more thing I want to show you, and that is that I had an email over the weekend from Christian. Is he in class? Oh yes, Christian. Wat was jouw probleem?
As iets ongerust ontpakt, dan probeer je op te seconden.
Zeg gou weer.
Kom ons sê, die reschedules en 50 milliseconden. Dan gebeur dit oor, soos hy doen die hele tyd oor 'n sekonde kwyt. So hy sal soos 8 keer uitvlieg.
En dan stop vir ewig.
Ja, hy sal dan later. Maar as dit skyn.
Hy spam dit.
Hy spam soos
ja. Ek dink miskien dit klink af my asof ek nie 'n probleem 100% verstaan nie. So in essence, you say if something's taking less than a second, it happens a lot until up to a second, and then it's normal pace. So why does it happen so quickly at the start? Is that the issue? Okay. Well, in that case, I know exactly what your problem is, and I sent you something back about your iterate routine in game, because it didn't look normal, but I know exactly what your issue is. I can help you now if you haven't solved it yet. And that's described on the webpage, but in essence, if you add something to the game, we may have talked about this in class as well. If you add something to the game, there's iterate, and that's fine. And there should be an add routine. Let's just make this a little bigger. somewhere in game there should be an add actor. So this is actually described in the next step. Let's just make sure. So step 2 is about making a super cat, and step 4 is about making a cat producer, which is basically where your problem comes in. So let's say the game has been running for 10 seconds. So all the items in my heap, they were in the heap originally, and somehow they executed and they rescheduled themselves. So at the moment, I've got my heap of things that must happen, and they all have times in the region of 10 seconds. So 10,000, 10,200, 10,400, all of that. Let's say one of these items in my heap is a cat producer. So it's supposed to happen at 10 seconds. I take out the cat producer. In fact, I will draw this on paper. Stop waving my hands about. Just need to find some pad, and I've decided to go back to big pads because, as it happens, we have a new scanner, and it's easier for the scanner to scan big documents. So let's just get this. Okay, right here. Can zoom in a little bit. Yeah, cool. Right. Oh, and we have this focus problem, but we'll just have to live with that. No, life is hard. Okay, so here we go. Today is the 6th. Here is my game start, and that's time 0. A lot of things have happened. And I've moved up to time 10,000. And at this point, I have a heap that contains a few actors. And the first actor, let's say, is a cat producer that's supposed to execute at time 10,001. And that's the first. Does it make a difference? No, not really. Okay, so that's the first event that must happen. So my game will remove the cat producer from the event queue. It'll execute it. What does the cat producer do? It does. What does the cat producer do? It produces another cat. So this cat producer will be taken out of the heap. This will happen in time 10,001, and it'll produce a cat. Here's a new cat that it's going to add to the heap. Let's say it's a normal cat. And the cat producer will reschedule itself, let's say, to execute again in 1 second. So its new time will be 11,001. Because it rescheduled itself to execute in 1 second. But that normal cat, that's a normal cat. Moving at normal speed. When I create a normal cat, what time do I give to it? What time do I give a normal cat? Well, there's code in actor that says when you create a new actor, always set its time to 0. So this normal cat will have time 0. All the other stuff in my heap have real times. I've got like 10, 200, 10, 100. This guy thought he was going to execute next after the cat producer. He was up next. There's a 10, 200 actor. There's the cat producer itself, which will again execute at time 11. Oops, I'm sorry. So there's this actor which wanted to execute at time 10,000, 10,100, and it thought it was next. Christian. There was another guy who wanted to execute at time 10.2 seconds, and the cat producer just rescheduled itself to execute at time 11.001 seconds. But now I've created the normal cat, I've added it to the queue with time 0, and game iterate will now look at this heap of things to do and say, well, the first thing that must happen is that this normal cat must execute at time 0. So the normal cat will execute, draw itself on the screen. It will rejoin the queue. It will reschedule itself at time, let's say 1,000, 1 second later. And if game iterate looks at this heap, it will say, well, what's the earliest thing that must happen? Well, this normal cat must happen at time 1,000. So I'm going to remove this normal cat. It will execute and reschedule itself at time 2,000. And it's still the earliest. This normal cat will keep on executing. It will get priority until it catches up with the other items in the heap. And that's wrong. I mean, the fundamental problem was that when I added the normal cat the very first time, I set its time to 0. But that was a mistake. It shouldn't start at 0. The normal cat's time should start at, well, whatever the time was for the cat producer. When I create a new normal cat, I should tell it, you must execute at time, well, whatever my time is plus a few seconds, plus a few milliseconds. So when you add something to the heap the very first time, it must not start with a time of 0. It should start at the current time. So we can change the add routine in game so that when there's a new actor, I can set its time to the current time. And now Java will complain because actors don't have a set time routine, and we can easily fix that. Or as I suggest on the web page, all the stuff is on the web page already. So as we suggest on the web page, you can just add it as a parameter to set heap. And then set heap will say, well, this is the time I want to execute, but this is measured from 0. So I'm going to add the current time to it, the starting time. And that'll fix your problem, Christian. Are you all happy about this? Brian?
So I have a different question.
Oh, well, just hang on for a second. Is anybody else unhappy about this? You all understand this easy peasy stuff? Okay. Yes, Brian, ask your question.
There is some other method with a capital B void type. And I'm not sure what it's doing for return.
Is that a question or a statement?
Question. Do you mind just explaining that?
Oh, okay. Can you explain? Can I explain some other method? You don't know what it's called, but there's a capital V void somewhere around it. Okay. So I'm going to undo these changes because they are really in a later version of this RVC framework. I'm just going to undo this change. So this is my pristine edition for the step 2. But we can go back to step 0, the original framework, to explain what you're talking about. And it's in class RVC. So this is RVC. It has a main routine, which just starts everything up. Basically, all it's doing is asking the Swing library, this thing called Swing Utilities, to start the app, in some sense. Start up the app, and this is the constructor. It has a few routines for creating the user interface, like make buttons, make button, make status, all kinds of stuff. Action performed, where it listens for button presses. It needs that as well. And then at the end, it has something called game task, which is an extension of this class, string worker void void. That's what you're talking about. Okay, so let's just gather our words. This game task has, firstly, it's a nested class. So it's defined inside RVC, and it's private, so only RVC can see it. And that's perfect because it ensures encapsulation. No need for other classes to ever see this game task. it's only RVC that's going to need it. This game task extends that other class called swing worker, and that's important because when you start up, when you use swing to make a user interface, Java starts a thread that'll listen for events. So this is a typical strategy for user interfaces. This looks wrong. I mean, this looks too bright. We should find more color. Maybe I should just switch off this little light. Slightly better. Never mind. Well, I think the light makes a difference is that sometimes in low light conditions it can be difficult for cameras to focus. But I'm not sure if that's the issue here. Never mind that. I think it'll be okay. So user interface. With swing. How does it work? Well, swing provides a lot of infrastructure, and part of that is basically a while loop that listens for all kinds of user events. So RVC is my class where I define my user interface. That's really my whole game. It's a class like that. And when I ask swing to start it up, what it does is it creates basically a while loop that listens for events. And this can be any kind of event. It can be a mouse event, or buttons being clicked, something typed on the keyboard, the operating system shutting down, the user moving a window or resizing a window. There's a whole lot of events that can happen that swing will manage for me. And I can say things like the following. I can say things like, somewhere I do this. Let's just see where. Give me a small second. I'll find it. Where do I make the quit button? Here we go. As part of my construction for the RVC class, I say, create this button and add something called an action listener to it. So there's an action listener associated with this quit button as it happens. And what it means is that part of my user interface is having a quit button here. And I'm adding a listener to it. So in this while loop, when somebody clicks on my quit button, this class will be called to tell it that you asked that you wanted to be informed of quit button clicks. You added yourself as a listener for this button. So somebody clicked on the button, and I'm now going to call you. And the routine that's called is called action performed. Here is the action performed routine, and it actually says if the source of this action, whatever it was the quit button, then I can quit the application. And this is a very useful framework because what it means is we can set up a user interface and we don't really have to do much. We can perhaps implement a few buttons, but we don't have to manage tracking the mouse, knowing when it clicked, resizing the window, relaying out all the buttons, all that. You can just set up the user interface and listen for the actions that you're interested in. But it also means that we don't have control. We don't have a loop somewhere where we execute. Everything happens in here in swing. And really, swing is very passive. It just sits there, waits for events to come in from the outside, and then it responds to them. If it's a window resize event, swing will handle that. It will resize the windows for us and lay out the buttons in their new positions. But if it's a button click event that we're interested in, swing will actually tell us about it. But basically, swing is in control, and it sits there waiting for something to happen. But our game is different. Our game also wants to be active. Cats want to move on their own. They want to move by themselves in some sense. So that's why we need a swing worker. While that while loop is executing, swing will execute our swing worker. And as it happens, we call our swing worker game task. It's a kind of game task. And it has one routine that is executed once, really. So it's called do in background. That's really the core of this swing worker. And what does do in background do? Let's just see. It has its own while loop. Just like the swing task, do in background has its own while loop where it simply checks, have I been cancelled? So while I haven't been cancelled and I can still do one more game iteration, I'm going to do that and do nothing else. So this while loop here will execute at the same time as that while loop there. This is actually something amazing for you guys. You've never seen this. It's probably the first time you see that you have two while loops that execute at the same time. It's not as if they're nested inside each other. If they were nested inside each other, then the middle one, the inner one, would execute all the time. And when it's done, it would give the outer one a chance to execute once, and then it strikes the middle one, the inner one again, and that executes a lot of times. And when it's done, it's the outer one's turn. They're not taking turns. These while loops are actually executing at exactly the same time in different parts of the code. So a while loop here that's waiting for events from the user interface. Another while loop here that's actually playing our game by executing game iterate, game iterate, game iterate, game iterate all the time. And game iterate is the part of our code that says, look at the heap. Is there anything else I have to do in the heap? If there is, take it out and execute that actor. Otherwise, sleep for a while. Okay, so this while loop will carry on until this task is cancelled, and then it returns null. And this task at the moment, at least in this version of the code, this task is cancelled in only one place, and that's when the user presses the quit button. Issue? So the swing while loop was executing. It detected an action. It detected that somebody clicked on the quit button. So it called this routine action performed in my RVC. And RVC said, oh, well, the user wants to quit. This is the time to cancel the game task and dispose yourself. So that means the swing while loop, button click, call action performed, oh, it's the quit button, cancel this worker and shut yourself down, dispose yourself. And the swing worker will also execute its while loop and it'll see, oh dear, the is cancelled flag is now true, so not is cancelled is false, so the while loop can't execute and it'll stop and it'll send back a null. So Brian, does that answer your original question, or? I mean, you asked me if I can explain it, and I think the answer is yes, I can say something about it. But is that what you wanted to know? So no. That's a polite way of saying no, you didn't answer my question at all. I'll go with it. What else did you want to know?
It's fine, I'll ask you later about the capital V void.
The capital V void. I had a feeling that that was your issue. It's just another way of saying void. And just like we have an int and a big I integer, and a float and a big F float, and a double and a big D double, we have this big V void, which is exactly the same thing as a void. It's an object that represents one single value, and that's the value null. Int can be 0, 1, -1, 2, -2, 3, -3. It can have many different values. So if I define a data type of type int, it can have many values, but void, data type of type void can only have one value, that's null. Oakley dokley. Right here. So there was one more thing I wanted to tell you about the project, and I shouldn't be talking about the project too much, but let's say that my solution didn't answer Christian's problem at all. So I'm very sure that this is the problem you're dealing with, Christian, but let's say that it wasn't, and I want to debug my program. Have you tried to debug a swing application? It's really tricky because things happen in real time. It happens quite fast. I just want to quickly show you that there's a way to slow it down. Here in iterate, we check what is the next thing that must happen. It's now 10 seconds since the game started, but this next thing must happen at 11 seconds. So I have to sleep for 1 second. Often I have to sleep for a few milliseconds only, and that's way too fast for the user to see what's going on the screen. Our application is running too fast. But it's an easy fix to say, let's slow this down by a factor of 5. Sleep 5 times longer than you would have. I'm not going to run it because we only have a super cat in this version. We're not going to see anything. But in essence, what I'm doing now is I'm saying 1 second should be stretched to 5 seconds. 100 milliseconds should be stretched to 500 milliseconds. Everything is slowed down. You could also say, I want to see what actor, oops, I've taken out of the queue. So in addition to going slowly, this will print if we're not executing a cat or a normal cat. We're not executing the screen updater. We're not executing the power generator. So this will print out on the screen what's happening as it happens. And it may be useful to say at the time that it's executing. So I'm going to take out the 5. I don't want things to go slow. In fact, I want them to go a little quickly so I can demonstrate to you what happens. But let's just have it run at normal speed. And there's a cat going across the screen. Okay, that's fine. At the end, I think it will be the end of the game. Oh, no, it's not. That's not yet part of this. Oh. And let's go back to Java, Eclipse. Uh-oh. It didn't print anything. Did it not sleep, or? Oh, sorry, my mistake. I changed the wrong thing, and I probably executed the wrong thing as well. Here we go. There we go. Never mind that. What I really want to see is this. So that's a printout of all the actors that are taken from the heap, along with what time that is supposed to happen. So if we start at the front, I can't scroll all the way up, but after 200 milliseconds, the screen updater updated the screen. It redrew the screen. And then it happened again. That happens quite a lot. And then at time 1 second, the power supply got a chance to execute. And it boosted my power a little bit. In fact, I think the game is now waiting for me to quit. But I just wonder if I can do this. No, I can't do that. Okay, the cat got me, never mind. So using this, you can actually trace through. So the power supply executed at 1 second, and then again at 2 seconds, and then again at 3 seconds, and then again at 4 seconds. Every 2 seconds, the power supply every second the power supply boosted my power. The screen updater executed quite a lot. Then there's also the SuperCat, which executed at roughly 1.6 seconds. And then again at roughly 3.2 seconds. And then again at roughly 4.8 seconds. And then again roughly at 6.4 seconds. So every 1.6 seconds, a supercat got a chance to execute. This will help a lot. One thing you can do that's fatal is to, in one execution of the execute of an actor, if you reschedule that actor twice, there used to be one copy in the heap, but if you, by mistake, reschedule one actor twice, then there will be 2 copies of the actor in the heap. Each of those will execute and reschedule themselves twice. Now there will be 4 copies, then 8, then 16, then 32, then 64. So if you make a mistake with rescheduling your actor, if you have a complex behavior in execute, and you reschedule twice, more than once by mistake, then you'll see that the queue grows exponentially, your game slows down, and suddenly it's only cats everywhere, cats all the time. Okay? So that's a bad thing that happened to me. I made a small mistake at some point, so you should watch out for that. Okay. So, anything else you want to know about the game? The project? You're keeping up step by step. Today I showed you step 2, and Wednesday I'll show you step 3. Okay, cool. So you're kind of happy. What did we talk about on Friday? Who was here? No one. Skulk. Did you or did you not tell me that you come to every class? Or did you stay quiet? Did you say that? You were lying, weren't you? Because you're speaking now. What did we do on Friday? Waar moet ons geëindig? Oh, okay. I can't remember. It's so long ago. Let's just see if we can find it here somewhere. So I think that is still fine, but I really want my other screen. Okay, let's just quit Eclipse because that's confusing me. And I really want to go to Firefox. Oh, there we go. Schedule, just hang on. I just want to get my little, no, schedule. I just want to get to my notes. Okay, well, that's linked list stuff. Oh, we ended with this. So this idea that there are many kinds of data structures we can use in computer science, and arrays and local variables are kind of static in the sense that you can somehow create a new array that's bigger than the previous array and copy all the values over, but it's not the same array. They're static in that you have to declare beforehand how big is this array going to be. Whenever you use an array, you must say how big it is going to be. Obviously, a local variable can only hold one value at a time. But often we want to have dynamic stuff, dynamic values, a dynamic number of values, and that's why we are interested in lists and all their little variations, all the things they can implement, like a stack or a queue. And we've only looked at singly linked lists, but there's also something called doubly linked list, but each node remembers who's next in this list and who's in front of me in the list, my next and my previous. So they point both ways. It's like holding hands. So a singly linked list, suddenly a metaphor is coming to me, it's like when you're standing in a queue and everyone in the queue puts their hand on the shoulder of the person next to them. And a doubly linked list is where they have their hands on both their neighbor's shoulder. So they're touching people in front and behind. I don't know why the people would be doing this. I don't know. Then we have rings, where the very last one in the queue, its next is pointing to the very first one. So the whole thing is linked together in a big ring. There's no beginning and end. If you go next, 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 you'll be going around the queue forever. And sometimes we have doubly linked rings, where you can go backwards and forwards. And sometimes this is really useful. And then I said, we want to talk about sorting. So we've already seen that if I have an array, I can use different algorithms to sort that. We looked at insertion sorting and merge sort. We also looked a little at bubble sort, but I really want you to forget about that. But we also looked at these sorted lists. I can have a list that's always sorted in ascending order. Whenever I add something to the list, I put it in at the right spot. Next year, you're going to look at all of this again, and the rest of this semester, essentially, we're going to look at a different data structure that's not even listed here. But today, just quickly, briefly, I want to talk about trees, because you're going to need this for the tutorial on Thursday. So what is a tree and how does it work? And we've already done trees. I mentioned that on Friday as well. We did trees for our other project, our first project. But we're going to start again. So, just briefly. I have a linked list. And inside I have a node. So my linked list really consists of a lot of nodes. It has more than that. It also stores the first pointer. And sometimes we've seen that we want to sort of point to the last element in the linked list as well. Because if you want to remove stuff or add stuff to the end, it's easy to have a pointer to the last. But basically, each node in my linked list stores a value. I'm going to call it item value. And it stores a reference to the next node in the linked list. So that's linked lists, and we're happy about that. But if we are dealing with trees, oops, I'm so sorry. I'm sure someone wants to sell me insurance. Just turn off the sound. Okay, if I have a tree, just as in the first project, I'm going to have nodes that can also store items. But in addition to that, they have a left child and a right child. So my tree is going to have some kind of root that I'm going to point to. And this will be a node. And it'll store some value. And then there's a left child and a right child. Oops. So there's a little tree that stores 3 values. One in this root node, one in its left child, and one in its right child. So, how do I insert new elements into the tree? We know how to insert into a linked list. How do I insert into the tree? Any ideas? Let's find someone with ideas. What's your name? Yes. Anton. What did you say twice? Okay, Anton. How do you want to insert into the tree? You don't want to insert into the tree. You do want to, but well, where do you want to insert? You don't know, okay? Well, let's translate that question to linked lists. Here is a linked list. Where do you want to insert into the linked list, Anton? Why? Why not the last one? You still have to what? Anton, YouTube, Anton is indicating that he just doesn't know. He's not using the shoulder shrug gesture. He's using the hands, folding hands, and slight tilting of the head. Can we insert in the front, Anton? Have we done that? When? When did we do that? When did we insert in the front? We've seen it in the past 2 weeks. Yeah, I believe you. I'm sure you know how to do it, but when did we do it? Okay, right. So sometime last week. Well, yeah, you're probably correct because that's what I said as well, and I'm probably correct. But what I really wanted you to tell me is that we did it for stacks. For the stack, we said that the first is going to point to the top element of the stack, the first element in the linked list. And then when we push something onto the stack, we put it right in front, and it becomes a new top. And when we pop something, we take it off the front as well. So the very front was for stacks. We inserted at the end of the list for queues, because things join at the end of the list. We take them from the front. And then we also, in the TUT, saw the sorted list, where all the values in the list are in sorted order. And then sometimes we insert it right in the middle. Do you agree, Anton? Okay, right. So now you're better equipped to answer my new question. Where do you want to insert in the tree? In the front, but the tree doesn't, you mean the top of the tree, it doesn't have a front. By the way, you're looking a little confused, just while you have time to think. I know it doesn't look like a tree, or it looks like an upside down tree. I mean, if you draw it the other way around, it makes more sense that, you know, each node is like a little branching point in the tree and look like that. Or I guess you could say it looks like a tree's root structure, but we just call them trees. So Anton, where do you want to insert? Well, now it's the bottom, okay? Why do you want to insert at the bottom? Start at the bottom and space out, okay. Well, I will tell you that you are incorrect and correct. It depends. I mean, that's the answer. It depends, just as in the case of a linked list, it depends on what you want to do with the tree. Do you want to start inserting things at the top and build the tree towards the bottom? And then we always insert at the bottom? Or do we want to insert stuff at the top and always press whatever is old down so that the freshest stuff is at the top of the tree? Or do you want to implement some kind of strange ordering in the tree? And most often, we want to impose some strange ordering in the tree. It's amazing, but most of the time we're dealing with trees with a special name. They're called binary search, oh well, we know that name, trees. And they have a special property. And the property is that if I'm a node, for node n, there is a special rule. It doesn't look very clear to me. I hate this. There's no way to adjust the exposure. Hang on, I just want to see if I can. There's nothing here. What's this? No. Okay. Never mind, we'll survive. Oh, here we go. Brightness. I want you to decrease the brightness. Oh, there we go. That's nicer. That's fine. So for node n, there's a special property that says, if I'm node n, I have a value. I'm storing a value. And the value of the children, on my left-hand side are smaller than my own value. So for node n.left.value is less than n value. All the nodes on my left-hand side, all my left children, are smaller than I am. They only store values that are smaller than I am. And the opposite is true for the right-hand side. So if I am node n, then my value is smaller than all the children, the values of the children on my right-hand side. So I'm a node, smaller to my left, bigger to my right. And I'm going to write an insert that will respect this. So we're going to write a function called public node insert node n item. Okay. I have to write code that will insert this value into the tree called n. N will be a tree like this, and it should send back the new tree. And more than that, we're going to use recursion. I mean, this is exciting stuff for you guys because you know recursion so well, but you don't know trees at all, so it's a combination of the known and the unknown. I'm going to stop in a few seconds, but I just want to write the first sentence, which I hope you'll find interesting. Okay, so if I'm asked to insert something into an empty tree, then I'm not going to use recursion. I'm just going to create one new node with this value and a null left and a null right, and I'm going to send that back. So if I'm asked, given an empty tree, to insert 3, I'm going to return a new node with 3. That is what I'm going to return. Oops. Now it's a little too dark. How do I get that little menu back? Oh, well. That's good enough. So on Wednesday we'll finish this, and then we'll talk about the rest of the work in the textbook. And I'll also show you step 3 of the project.